Welcome to Maths with EJD. We continue with real analysis as we look at the fourth video on completeness of real numbers. Okay, the content to be considering here will be about some axioms like the least upper bound axiom, nested interval theorem, monotone convergence theorem, Bolzano Weierstrass theorem, and Cauchy completeness. So let's move on straight to talk about the axioms and theorems, starting with the very first one, least upper bound or LUB slash supremum axiom. So this one says that every non-empty set S, which belongs to the set of real numbers that is bounded above, has a least upper bound, or what you call a supremum. So that's sup S belonging to R. So this simply tells us that if you have a set of numbers that are proper subsets of real numbers, and that set is actually bounded above, it has a maybe as it's going, it's approaching a particular value. That is the idea of boundedness, right? So if it is bounded above like that, it has a least upper bound, or what we call a supremum, called sup S, which is also a real number. So in short, we are saying that a non-empty set of real, a non-empty set S, which contains real numbers, that is bounded above, has a least upper bound, a supremum that is also a real number, simply. So bounded above here means there exists a particular big M that is a real number with x less than or equal to m for all x belonging to S, right? So it means that if you take any x belonging to S like that, there's a particular M such that any particular value x you take from that set S is always less than or equal to M. That means it has a boundary at the top, which is M, basically. Okay. In this case, we can say that a particular number alpha, a particular element alpha, is the supremum S if and only if the following conditions hold. First of all, if any element x in the set S is less than or equal to that alpha, that talking about the supremum now, for all x belonging to S, and two, for every epsilon that is greater than 0. Like I've always said, an epsilon is actually, I mean, the idea of epsilon is a positive number that is very small, right? It is very positive, but maybe it's close to 0, but it's very small, most likely close to 0, but it's guaranteed that it's positive. So for every epsilon greater than 0, there is a particular x which belongs to the set S, with the difference between the supremum and the epsilon being less than x, like that. So that simply is telling us that the alpha, which is the supremum of S, is actually whatever, any kind of x you take plus a little bit more, so that alpha is always bigger than that x. That is the least upper bound axiom. Of course, least upper bound is also known as supremum, like you have seen there already. So we go to the next one, which is the nested interval theorem. Nested interval theorem. Now, if you have a closed interval, I think in one of the previous videos, you had seen the idea of a closed interval. The idea of closeness means that the elements at the top, the first element and the last element, all belong to the set because it's a closed element. So if the closed interval an, bn is a sequence of closed non-empty bounded intervals with the following. Now you have an to bn. So you have a1 b1 to contain a to b2, which contains a3 b3 and so on and so forth, until you now have that the limit as n goes to infinity of bn minus an is equal to 0. So as you're moving on, you would see that the difference between b and a is, as n is becoming bigger and bigger, is actually, that difference is approaching 0. Then in that case now, you can say that all the intersections of all the subsets like that contains exactly 1 point. So there's only 1 point common to all of the A1s and B1s if all the conditions above actually get to hold. I think we're going to see the proof later on in this in the video. Now let's talk about monotone convergence theorem, MCT. So a monotone sequence. Okay, well, of course, since we're talking about monotone convergence theorem, so I took it upon myself to actually explain the idea of what monotone means. So a monotone sequence is a sequence of numbers that is either consistently increasing or consistently decreasing. So if you have a sequence 1, 2, 3, 4, 5, and so on and so forth, that is a monotone increasing sequence. If you have a sequence 10, 9, 8, 7, 1, that's a monotone decreasing sequence. As simple as that. That's the idea of a monotone sequence. So then we have a theorem associated with monotone sequences called the monotone convergence theorem, MCT. So every monotone and bounded sequence of real numbers converges, right? Every monotone and bounded sequence of real numbers converges. So if you have any sequence that is consistently increasing, or a sequence that is consistently decreasing, and it is bounded, it has a boundary, then you can say that it converges because that boundary. So there's something about boundedness and convergence, right? So there's every likelihood that the convergence is towards that boundary, right? So if you have xn, if you have a sequence xn which is increasing and bounded above, it is increasing, right? But it is bounded above. It is approaching the particular limit above. Then you can say that xn approaches supremum of all the possibilities of x, such that n is a natural number. All right. And then, so it means that xn is approaching the particular natural number, which we can consider as the supremum of xn. Then if xn is decreasing and bounded below, then we say that xn is approaching an infimum xn, such that n is a natural number also, right? That is the monotone convergence theorem. Now we move on to the Bolzano. I mean, these theorems, as you can see, they are basic ideas, but because they are not, we are not writing down numbers. They may look like they are complicated or something, but they are basic concepts that we need to, just like we said from the beginning, right? That real numbers, I mean, real analysis helps us to, think in abstraction. It can help you to conjure ideas, to figure out things in abstraction. Then we have, but these are real things actually. So you have the Weierstrass theorem, which is very simple. It states that every bounded sequence in the real number system has a convergent subsequence. So if you have any sequence for a set of numbers that are real, they always have a convergent subsequence. So if from the sequence you extract a subsequence from that, so that subsequence will be convergent, right? As far as the original sequence itself is a set of real numbers that is bounded, right? So the idea of boundedness, like I said the other time, is the fact that the numbers are moving towards a particular value. Then we talk about Cauchy completeness. A sequence xn is Cauchy if for every epsilon greater than 0, there exists n such that the absolute value of the difference between xn and xm is always less than epsilon for every m and n that is greater than or equal to that particular value n, right? So you have a Cauchy sequence xn. So it means that for any xn you take, if you just take another x sub m like that, so the absolute value between xn and xm is always less than that tiny epsilon, which is a positive value, by the way, for every m and n that is greater than or equal to n. So that's like that's the idea of Cauchy completeness. So of course, to finish it up, the completeness part is that in real numbers, right, every Cauchy sequence converges to a real number. So in the set of real numbers, every Cauchy sequence converges to a real number. That's basically the idea. So if you look at this now, this small m and this small n now is all for every small m and n that is greater than or equal to that n that we say exists, right? The absolute value of xn minus xm is always less than that epsilon. So let's look at some of the proofs. So the first one is about the monotone convergence theorem. So we want to prove the monotone convergence theorem from the lower upper bound, right? So imagine let xn be increasing and bounded above, right? So, of course, the increasing part is what makes it monotone. And then being bounded above talks about the idea of lower upper bound. So let xn be increasing and bounded above. Then we now say set S. If you have S now, to be the collection of all xn such that n belongs to the set of natural numbers. So by lower upper bound, right, we have alpha, which is the supremum of sup S, exists like that. Okay, and then if we fix epsilon to be greater than 0, since a minus epsilon is not an upper bound, then there exists n with xn, which is greater than alpha minus n. So the whole idea of this is that, so whatever xn you take, it's never equal to alpha, because because you need some small value to add to xn for it to be up to alpha, right? So like that. So you now say for n that is greater than or equal to n now. So we have xn to be less than or equal to xn less than or equal to alpha, which implies that you have 0 less than or equal to alpha minus xn less than or equal to alpha minus x big N, or less than epsilon, like that. So in that case now we can say that xn approaches the supremum, the sup s now, which has been said to be alpha. So in this case now, we have been able to prove the monotone convergence theorem from lower upper bound. So it's all about taking this thing step by step, the logical steps to approach what you need to get. Then talking about the Bolzano Weierstrass bounded sequence, right? So let xn be bounded. So if xn is bounded, so it means that it has a supremum, right? Then we say that we can say xn it belongs to the closed interval A1 to B1, right? So if you bisect A1 and B1 and choose half containing infinitely many terms, and we call it A2, B2 now, So it's like we're selecting half of all of that, right? Bisection means dividing the whole sequence into two, and we choose the half containing infinitely many terms. Now we can continue recursively and we keep bisecting. So we construct nested intervals AK, BK with length B1 minus A1 divided by 2 raised power K minus 1, right? So that's like the number of times you are doing that. So by the nested interval theorem, there exists a particular X star which belongs to the intersection of all the possible AKs and AK, BKs that you will ever have, right? So then you can now choose a subsequence, say XNK, which belongs to AK, the closed interval AK, BK. Then in that case, we can say the absolute value of xnk minus x star, this x star is now less than or equal to bk minus ak, and that difference approaches 0. So in that case, we can then say xnk approaches x star. So I think that talks about the Bolzano Weierstrass theorem, which talks about the fact that if you have a bounded sequence, then any subsequence for me to take is that actually approaches where is that now? So any subsequence you take from it is actually convergent. That's the idea there. So let's look at the forward and backward proof of how a Cauchy sequence is convergent and how a convergent sequence is Cauchy, right? So, in this case now, because we have to prove it two ways. So we want to prove that Cauchy is convergent and that convergent is Cauchy. So, let's look at how a Cauchy sequence is convergent. So let xn be Cauchy. So we're assuming that xn is Cauchy, right? Then because it is Cauchy, then it is bounded statement. Then by the Bolzano-Weierstrass theorem, it means that because it is now bounded, and Bolzano-Weierstrass says that if you have a bounded sequence, then that sequence has a convergent subsequence. So first of all, if xn is Cauchy, if it is Cauchy, then it is bounded. Then by Bolzano-Weierstrass, it automatically means that it has a convergent subsequence xnk, and because xnk is convergent, that means that xnk approaches a particular limit L. So for given epsilon that is greater than 0, right? So you want to choose a particular value n such that the absolute value between xn minus xm is less than epsilon divided by 2 for mn that is greater than or equal to n. All right. So we can now pick the subsequence xnk. So I mean, for that, relating to the subsequence now, if you now have a particular nk greater than or equal to n with the absolute value xnk minus the limit less than epsilon over 2, then we can say for all n greater than or equal to n, the absolute value of the sequence xn minus the limit, right, is always less than or equal to xn minus the subsequence plus. So this is us, like, I mean, if you open this up now, it's like you're saying xn minus xnk plus xnk minus L. So we can now break that apart to say that absolute value of xn minus L is less than or equal to xn minus xnk plus xnk minus L. So if you cancel this out, it's more or less like you still have xn minus L like that. So to make that happen, so you now have xn minus xnk plus xnk minus L less than infinity, I mean less than epsilon. So if that happens, then we say that xn is convergent. So it converges to a limit L. So that is us proving that Cauchy is convergent. Now, how do we prove it backwards that convergent, a convergent sequence is Cauchy? All right, so this is simple. We just say every convergent sequence is Cauchy by the triangle inequality. So you can see that right here now. So by triangle inequality, you notice the idea of triangle inequality, that absolute value of xn minus L is less than or equal to absolute value of xn minus xnk plus absolute value of xnk minus L. All right. So every convergent sequence is Cauchy by the triangle inequality. And what makes it Cauchy? Cauchy, it is bounded, and then it has a convergent sequence that is, I mean, it is bounded basically, right? So if you can prove that, if you can start from the fact that it is convergent, then you go back to the fact that it is Cauchy. Okay, so let's look at some worked examples. So let's talk about bounded non-convergent sequence. Example, imagine that you have xn equals minus 1 raised to power n. All right, that means when n is 0, you have 1. When n is 1, you have minus 1. When n is 2, you have 1. When n is 3, you have minus 1. So at the end of the day, you have this, you have some kind of I don't know, maybe periodic is not the word. Basically, this sequence has just two terms. So it is bounded. So this is simply a bounded sequence starting from minus 1 and ending at 1. So it is bounded by minus 1 and 1, right? So, and if you take any subsequence from here, so if you take subsequence x2k starting with 1, it ends up with 1. If you take an odd subsequence, and for an even subsequence, that means if you take power 0, power 2, power 4, power 6, and so on, you always get 1 like that. Then if you take odd subsequence, say power 1, power 3, power 5, you always have minus 1. So in that case, we can say sequence does not converge since it has two different subsequential limits. So if you pick two different subsequences, if you pick an even subsequence or another subsequence, they converge to different limits. So in that case, you say the sequence does not converge because it converges to two different limits. Okay, so that's a bounded non-convergent sequence. So you can have a bounded sequence that is not convergent. Okay, then we go for existence of square root of 2. So we want to prove that the square root of 2 exists via the lower upper bound theorem. So first of all, define S, big S, which is the collection of all positive x such that x squared is less than 2. Okay? All right. So it means that you are looking for all possible values of x such that x is less than the square root of 2. You know, if you take the square root of both sides, right? So it means you're talking about all the possible real numbers. Okay, we haven't talked about real numbers here right now. So maybe you're talking about every number before 1.41414141414, which the square root of 2 does represent. Now, once you have that in place, the next thing is you're saying 1 belongs to that S. Of course, 1 belongs to this S, right? Because square root of 2 is 1.414 and all that. So 1 belongs to that S. So S is not empty. At least that. So for you to, all you need to prove that S is not empty is to find a part that S has at least one element. And we are very sure that 1. So 1 satisfies this expression that, 1 squared is less than 2. That's guaranteed. So so we want something greater than 0, but x squared less than 2. So 1 perfectly fits into that. So if you now say for x greater than 2, so we know that x squared is greater than 4, and 4 is also greater than 2, right? So we say that S is bounded above. So S has an upper bound for sure. Because in this case now you need x greater than 0, but x fulfills this condition now. So at the end of the day, so you have all this. So now if you say So if you now say let alpha be the sup S, that's the supremum of S, then let's see case one. If alpha squared is less than 2, then you pick a small epsilon greater than 0. Then you say that alpha plus epsilon squared is less than 2. And in this case now, we see that that contradicts the fact that alpha is the supremum of S when we pick alpha squared less than 2, because this is supremum, right? Then for case 2 now, if alpha squared is greater than 2, we pick small epsilon less than 0, and then we have alpha minus epsilon squared greater than 2. And this also contradicts the fact that alpha is equal to the supremum of S. So thus we say that alpha squared less than 2 doesn't work, alpha squared greater than 2 doesn't work. But we can settle for the other situation where alpha squared is equal to 2. And then we say that alpha is square root of 2. So with this, we have been able to prove the existence of square root of 2 via the lower upper bound theorem, like that. Then let's talk about, okay, okay, this talks to the end of the whole thing. So let's talk about equivalence of completeness. So now we can see that everything we have considered so far is connected in one way or the other. So the following are equivalent in real numbers. So we have least, so all these things, all these theorems we considered and axioms, they are equivalent when we talk about real numbers. So least upper bound axiom, nested interval theorem, monotone convergence theorem, Bolzano Weierstrass theorem, Cauchy completeness. And there's an implication chain that tells us that lower upper bound implies monotone convergence theorem. Monotone convergence theorem implies nested interval theorem. Nested interval theorem implies the Bolzano-Weierstrass theorem. And the Bolzano-Weierstrass theorem implies Cauchy completeness. And Cauchy completeness implies LUB. So you see, it's a kind of cycle that they are all interconnected like that. So this whole thing, these theorems are interconnected. They have they're equivalent basically. So that's why you can always establish connections between all these 5 axioms and theorems. So this brings us to the end of the completeness of real numbers. Thank you so much for listening. Let me know how helpful this is for you. And if there's something you'd like me to do as far as this topic is concerned, feel free to let me know in the comment section, either on Facebook or on YouTube, right? Having done that, don't forget to subscribe if you haven't done that already. If you have subscribed, thank you so much. Don't forget to hit the notification bell so that you can always get alerted each time a new video is released. And having subscribed and hit the notification bell, don't forget also that you can take it a step higher. You can become a member of this channel by clicking on join, and you find 3 levels of membership that will confer you some extra privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.